Tank level control is the classic process control example. Every beginner gets the hysteresis wrong on first attempt. Without hysteresis, the pump cycles on and off every few seconds and eventually burns out the pump and the contactors. This video walks the two-setpoint hysteresis pattern, the analog input scaling, the latching coil that implements the hysteresis, the high-high and low-low alarm rungs, and when to use this versus PID control. By the end, you have a tank-level rung that does not short-cycle. First, the single-setpoint trap. A beginner writes a rung that says, if level is below 50%, start the pump. The pump starts. Level rises through 50%. The rung condition goes false instantly. The pump stops. Level oscillates within a small range and drops back below 50% within seconds. The pump starts again. This is short cycling. The pump and the contactors are not designed for it. Equipment dies in weeks instead of years. Every controls technician sees this rung at least once in their career, usually written by a previous engineer who left before the consequences arrived. The fix is the two-setpoint hysteresis pattern. Define a low set point, say 40%, and a high set point, say 60%. The pump starts when level falls below LOW. The pump stays on until level rises above high. Then the pump stops. The pump stays off until level falls below low again. The 20% deadband between low and high is the hysteresis. The pump cycles slowly, once every few minutes or hours, depending on the tank size and the inflow and outflow rates. The pump survives. The contactors survive. The plant runs unattended for weeks instead of breaking every shift. The latter implementation is a classic seal-in latch with two comparison inputs. Rung condition, level less than low, or pump running and level less than high, drives the pump coil. Two comparisons separated by a parallel branch in the ladder. The first comparison starts the pump when level is below low. The second comparison is the seal-in. It holds the pump on while level rises through the deadband. The second comparison drops when level exceeds high. The seal-in releases. The pump stops. Same shape as the motor seal-in pattern from the ladder logic video, just with comparison instructions instead of normally open contacts. The analog input scaling. The level sensor is usually a 4 to 20 milliamp loop transmitter or a 0 to 10 volt differential pressure sensor. The raw analog to digital converter count needs scaling to engineering units. Alan Bradley uses the SCP instruction, scale with parameters. Siemens has the scale_x function block. Both convert raw ADC counts to a real number level percentage. Once scaled, the comparison rungs use the percentage directly. SCP from 4 to 20 milliamps mapped to 0 to 100%. Then the rung condition is level less than 40 as a clean readable threshold. The scaling instruction is the cleanest place to put the unit conversion. Putting it in every comparison rung is a refactoring nightmare. Real plant tanks need alarm rungs in addition to normal control. A high alarm. Level critically high, force shutdown. Set the threshold above the normal high set point by a safety margin. If normal high is 60%, high might be 90%. A low alarm. Level critically low, force shutdown. If normal low is 40, low might be 10. Both drive critical status bits that the HMI picks up and the operator notification system displays. The alarm rungs are independent of the normal control rungs. The control rungs handle the routine cycling. The alarm rungs handle the failures. Sensor stuck. Pump dead. Outflow valve seized open. Each of these scenarios produces a runaway level that the alarm rungs catch. On-off hysteresis versus PID. When to choose. On-off works when the process tolerates level oscillation between low and high. Water treatment tanks. Holding tanks. Most utility applications. The math is simple and the tuning is trivial. PID gives stable level at a tight target set point. Required for precise dosing. Pharmaceutical mixing. Pressure-sensitive process applications. PID needs a variable speed pump or a control valve, more sensor cost, more tuning, more PLC processing. For most tank-level applications, on-off hysteresis is the correct answer. Reach for PID only when the process actually demands tight set-point control. Build the tank-level hysteresis rung at plcsimulationsoftware.com. The free tier includes a tank-level simulation with analog input scaling, two-setpoint hysteresis, and alarm rungs. Run it. Adjust the set points. Watch the pump cycle slowly instead of bouncing every second. This is the last video in the current calendar window. The review checkpoint is next. Based on the data, the cadence either continues or pivots. Either way, the simulator stays free. Subscribe to find out which direction the channel takes from here. See you in the next one.